Welcome to the fourth class of the Archimedes Academy by IMSystems. In the previous two classes and this class, I'm discussing the three most common drive types in the robotics industry. And last times I discussed the cycloidal gear and the strain wave gear. Today we're going to talk about planetary drives, a very old technology that has been invented hundreds of years BC, not of course to make robots, but to simulate the solar system and have planets revolving around the sun at the right speed. So let's talk about this ancient technology. And first, I want to discuss how it works. If you have this drive, you already see why it's called a planetary system. You have this sun with planets going around it and this outer ring. It looks quite simple, but it's actually quite hard to explain. So there are a couple of things you need to know first. It's quite a list of terminology we have today, so bear with me and let's go. Components of a planetary drive. Two of them, I already mentioned them, are quite easy. We have the sun wheel in the middle and the planetary wheels that go around it. Those planetary wheels are held together by a carrier, and that also makes sure they remain equally spaced. And then there's the inner ring gear. According to some, we prefer to call it the annulus on the outside. And before we continue, now it's time to first go into some basic physics classes. I want to talk about the moment, or torque, because that's calculated by the force times the distance. And you've maybe also heard me say that a torque is pretty much the rotational force in an earlier class. Well, that's what it is. And moments can counteract each other and balance each other out. And that's what you typically see in a seesaw. For example, this guy is twice as heavy as the one on the left, who has a load of 500 Newton meter at a 2 meter distance. And this one has 1000 Newton at a 1 meter distance. If you do this multiplication of 2 times 500, you will end up at 1000 Newton meters. And 1 times 1000 also is 1000 Newton meters. And that's where you get a balance. These moments you see in your everyday life without realizing it. And we use them a lot in levers, especially the first class, as we call it, where there's a fulcrum in the middle. You apply a force somewhere to move a load on the other side, just like that seesaw. Another example is a plier, where in the middle you have that fulcrum and you apply the load on one side, or the force on one side to grab a load. You can also move things around a little bit and place the fulcrum at the end. And with the load in the middle, you get the wheelbarrow. There's also a third class that's less common because it doesn't make your work lighter. Over here, the fulcrum is at the end and the load at the other end, and you in the middle are going to apply your force. Some muscles of us work like that, but there are some use cases. You don't make the work lighter, but you get more control over what you do. So for example, in tweezers, you also apply load in the middle, and it gives you the control to remove a splinter. And now we know what levers are. I also want you to know that that also applies to gears. Gears are also just levers. Just over distance, a certain force is exerted. Now you know this, it's also time to talk about how we are going to call the functions of the components. Because there are many gears rolling, but there's always one gear that drives everything. And that's what we call the input. And at the output, that's where the load is exerted. But there's also always a component needed. That's the ground or fixation point. You will hear me say ground mostly. And with this, I can finally explain all the functions of the picture you just saw. So the annulus on the outside is standing still. So that's the ground. The sun wheel at this moment is the input, and the planets are connected to the carrier that goes out to the output. Sounds simple. It's slightly more complicated because you can switch these roles around. For example, here in the second one, we now chose to put the sun fixed and then have the carrier as an input and the annulus as an output. Another option here at 3 is that you have the carrier fixed with the sun moving as input and the annulus moving as the output. Calculating the gear ratio is also different for all of these things, and I will not go over them all, except for the last one, because that will be relevant in later classes about the Archimedes drive. The gear ratio is very simply calculated by taking the teeth of the outer of the annulus, and dividing it by the amount of gear teeth of the sun. So now you know how the planetary drive works and how the ratios are calculated. Time to talk about the advantages and disadvantages. So why would you buy a planetary drive? Of course, it's very, very, very cheap. That's why a lot of hobby robot builders use it to make their robots. And also, it's top of the game in efficiency. It's at least 90%, but if you have a very good one, it can go to 99 point something. Then, because of that efficiency, it's also backdrivable and not just a little bit. You can put 5 in a row and drive them all back. And then there's also a high torque density. There's, of course, there's, however, a lot that also to dislike. It has a low precision, especially due to a lot of backlash, and that's why you will never see it in a high precision system. Also, low gear ratios are only possible, so we're talking about typically 5:1 to 30:1, and that's about it. And with this low gear ratio, you can go higher, but you need to stack them, and then you don't have that torque to weight ratio anymore. Then there's a very loud noise that comes off of it, and limited durability with high maintenance. So if I can summarize it, it is a drive that's very cheap and very efficient if that's what you're looking for. But otherwise, people typically go for a cycloidal or a harmonic drive. These were the 3 classes explaining all 3 drives there are. And next 3 classes will be focused on explaining how the Archimedes drive works. Thanks for watching and see you next time.